wanted to take a look at was describing the transformation. So I'm going to do both 9 and 10 on these. So we look on the inside first, and we're doing the opposite of that. Then we're going to look out front. In blue, there's nothing happening out front. There's no negative, which would tell us to flip. There's no number that would tell us to stretch. So we're not going to have to write anything for our blue. And then in green, that's my last step. So for this, there's only 2 steps. There's only 2 transformations. The first is removing, remember, we're going the opposite. So even though that's positive 3, when we're inside the parentheses, we're going opposite. So we're going left 3. And my second step is to move up 2. You're going to see how that affects a graph in just a moment. Okay, so for this one, we don't have a flip because there's no negative out front. We don't have a flip, but we do have a stretch. So we always start on the inside, and we're doing the opposite. So our first step is left 4. Our second step is going to be a stretch of 2. And our third step is going to be down 2. Okay? So you'll see how those work in just a moment. Really quick, I just wanted to do maybe a couple problems here for finding the zeros. So that was if we made y 0, we would have x minus 4 squared minus 1. So we're trying to get this by itself, which means I'm going to move that minus 1 first by adding it to both sides. So 1 equals x minus 4 quantity squared. That whole group is being squared. And now I have to get rid of this second power, and I get rid of a squared by taking the square root. That cancels that out. But I also have to take the square root on this side. So the square root of 1 could be positive 1. Positive 1 times positive 1 makes 1. It could also be negative 1. Negative 1 times negative 1 makes a positive 1. So it could be either one of those. So I'm going to split my equation up so that I have x minus 4 equals a positive 1, and x minus 4 equals a negative 1. And then I'm solving both of these. And so those are my x-intercepts. X equals 5 and x equals 3. So we could use those to graph. Okay. Let's switch gears again. I know this is kind of a rapid fire today, but I'm trying to get through Unit 14 so that we can move into our next unit. Let's talk about the transformations here for a moment. This is in vertex form. So our transformation, we know that it's moving left. Oh no, well, it's negative, so we're moving right 2. So our first step is right 2. And then we look out front. And our second transformation is we're doing a stretch of 2. And then our third thing that we're talking about is this whole graph is going to move up 1. So I'm going to show you 2 ways that we can do this. So we could graph. The idea is that a parent function for a quadratic, so that's before any of these changes are made, we would have the function y equals x squared. That's the most basic, and it would look like this. I'll show you in red. Y equals x squared would look like this, and I'll show you how these numbers correspond in just a moment. But this is what our parent function would look like. This is kind of like unchanged, the starting place before any changes take place, before we move anything right, before it stretches 2, before it moves up 1. So these are our directions for what's happening to our parent function, and this parent function stays the same every time. So this is our starting place every time, and then we kind of morph it using this. So here's our parent function. If I were to write a table for our parent function, because on our graph it's just a visual representation of our numbers or of what's happening for x and y, and I use -2, -1, 0, 1, and 2. In math, these are kind of like our 5 favorite numbers. If I were to plug in a -2 to x, that would mean -2 squared, and it would get us a +4. If I were to plug in a -1 to x, that would mean -1 squared, and that would give us a +1. If I plugged in a 0 for x, 0 squared is 0. If I plugged in a +1 squared, it's going to give us a +1. And if I plugged in a +2 squared, it's going to give us a +4. So do you notice that with these base kind of quadratics, if I have a negative number here that I'm plugging in, when we square that negative number, it ends up becoming positive for our parent function. So that's what gives us this. -2, 4. If I go 1, 2, there we go, up to 4. There it is right there. -1, 1. So if I go -1, +1, 0, 0, +1, +1, +2, +4. Not shown on my table is what would happen if we did 3. 3 to the second power is 9. -3 to the second power is also 9. So that's our transformation, or our parent graph. So let's talk about the transformation. In green, I wrote right 2, and I'm going to change this color here. You'll see why in a second. Let's use blue. So in green, if I move right 2, I could take each point, and I'm going to get rid of these ones because we'll just work with our 5 favorite. If I were to move each point right 2, I could go 1, 2, and have a new green point right here because I moved it twice. Same thing with this one. 1, 2, new green point. 1, 2, a new green point. 1, 2, a new green point on top of that old red point. 1, 2, a new green point. So I'm going to get rid of my kind of counting lines that I used to show you where I was moving. And do you see that now my red parabola just shifted over 2 to become my green parabola? Okay, so a stretch of 2 means a vertical stretch. So we're going to take whatever the y value is of our green now. I know this seems kind of crazy. We would normally in class have like a lot of time to practice this together and work on it and build our skills, but we're just going to see it a few times over the next several days, and then that will hopefully familiarize you with it a little bit. So for a stretch of 2, I'm going to do that in blue. I'm taking the y value. So the y coordinate for this green point right here, this y coordinate is 4. A stretch of 2 means I'm going to multiply that y coordinate by 2. So 4 times 2 is 8. So my new point is all the way up at 8. This probably seems crazy. Down here on my green point, the y value is 1, so I'm saying 1 times 2 because it's a stretch of 2. And that gives us 2, so my new blue point is right here. 0 times 2 is 0, so that's not moving. I'll put that over the green. And then you could reflect these if you wanted to, but it's the same thing, right? Now, we've been calling it a stretch of 2 for a long time, but do you now notice why it's a stretch of 2? Look at how much longer. Look at it's like we grabbed our green parabola and stretched it out to make that blue parabola. So that's a stretch of 2. And then our last step is up 1. So now in purple, this will be my last part here. I'm going to take every blue point and move it up 1. In our Algebra 2 trig class, which is, we do transformations in there too, but they're a little bit more involved, and we're using more than just quadratics. We're using all kinds of different functions. But in our Algebra 2 class, what we would do is we would do all these, and then what a lot of the kids like to do was then they would take their eraser, or really, I mean, what you could do is just put your parabola through your final one. There you go. We did a lot of color coordinating and stuff. Some students did just go through and erase all of the other colors that they had so that that was it. But if you were to leave this, that'd be fine. Seems crazy, right? I'm going to show you a different way. Kind of, actually no, I'm going to show you one more of the same way, and then that's going to be it for this video, and I'll show you a different way in the next class session. Okay? So I'm going to list my transformations. I like color coordinating, so I have my first thing's going to be, got my marker here. Our first step is going to be right 2. We do have a flip. This one's going to be fun. Okay, so an x-axis reflection. I'm going to flip my points first. Steps 2 and 3 are interchangeable. So for step 3, I'm going to do a stretch of 2, which means I'm going to multiply whatever my y value is by 2 to get a new y value. Stretch 2. Did I add an extra t in there? Nope. I'm good. Stretch 2. It's real early in the morning and I have a newborn, so not so good on the sleep and focus. Okay, and then my last step I'll do in purple. Number 4. Nope. Number 4, which is also to move everything up by 4. So I'm going to use my parent function. Remember, those are my 5 favorite numbers. If it was just y equals x squared and no extra stuff going on, we would have a table, and we would have -2, -1, 0, 1, and 2, and these would be the numbers that correspond. So I'm going to plug those in red. I'm going to start with red. That's my starting point. So here's my parent function. It's pretty general across the board. There we go. So there's my parent function. So now I'm going to start moving all of my red points right 2, and I'm going to show you that in blue. So we're moving right, and you can work from left to right. 1, 2, that's that one. 1, 2. So the whole thing moves right 2. Now I have a new parabola right there in blue. A flip means I am going to flip over the x-axis. Sometimes you hear me call it an x-axis reflection. That's really what the technical name is. So I'm going to take each point and I'm going to reflect it over the x-axis. So I'm going to go 1, 2, 3, 4, 1, 2, 3, 4, and put a new point in orange. I'll put a new point down there because we flipped it over. Same thing here. If I flip my blue, 1, 1. Now this one is staying the same. Think about a spot on the mirror. It's not really, it's on the mirror. It's not going anywhere. I'm going to reflect my other 2 points real quick. Okay, cool. So I did my x-axis reflection. Now I'm going to stretch 2. This is going to bring some of my points off of the graph, but that's okay. I'm only using my orange. And I'm going to use green here to stretch 2. So if I'm sitting at -4 right here, I'm going to multiply that by 2 and get -8. So this point is going all the way down to -8. Same with this point, all the way down to -8. I don't have enough room to do that. So those are just off the graph. No worries. For this point, I can do -1 times 2, and I get -2. So that's going to stretch to right here. Same thing over on this side, and 0 times -2. I'll show you a more mathematical way. This is kind of a little bit more mental math that some people may prefer, but oops, I'm not done yet. Okay, we stretch 2, and now we are going to move up 4. So actually, let me graph these, because these are, okay, so if -8's down here, I'll have a point down here somewhere at -8, 7, 6, there's -5, okay? And I'd also have a green point down here, because you'll see when we shift this whole thing up, we might make it onto the graph. Okay, up 4. So in purple, I'm going to move every green point up 4. 1, 2, 3, 4. Yeah, see, we made it back onto the graph. 1, 2, 3, 4, back onto the graph. 1, 2, 3, 4. 1, 2, 3, 4. Sometimes you'll overlap points. It's fine. 2, 3, 4. Okay, so I moved all of my purples. 4. I'm going to get rid of these squigglies though, because they're kind of, there's a lot going on. There are a lot of points here. If you notice, it's not really mathy. I mean, the only math we did was multiply by 2 to stretch. But it's not super mathy. So I'm going to show you a different way in our next lesson where we're using the tables. So if you didn't really like creating a bunch of different points and then just changing them one at a time, if you didn't like that, then you may prefer the other way where we're using a table. But again, the whole purpose of Unit 14 is to show you how many different ways there are to graph a quadratic. And that's graphing from standard form, from vertex form, doing all kinds of different, just graphing quadratics and how are they affected by the numbers and those kind of things. What do all the numbers mean? So I hope this finds you well, and we'll be diving into this some more in our next lesson.